Okay, when we first looked at momentum, we talked about how Newton really devised those laws of motion in terms of momentum, and how momentum was very related to forces in those laws of motion. Momentum itself, the inertia of a moving object, the difficulty and the resistance of changes in object's motion is sort of related to Newton's first law, the resistance of change in motion of an object itself. Newton's second law had to do with the impulse idea. If we apply a force over a certain amount of time, we're going to change its motion. That means we're going to change its momentum, and hence we've discussed the idea of impulse. Well, let's now look at Newton's third law and see how that also relates to momentum. And to do that, we're going to look at the momentum of a system. Now, it's very important to understand what a system is. It's pretty straightforward, but it is something we need to define. A system is all of the objects that are involved in an interaction. All of the objects that are part of a force or forces that are interacting with them. So the system is all objects in an interaction. And typically, we think of an interaction between two objects. We can now have an interaction that involves more than two objects. So 3 cars crash together. Those 3 cars are part of the system. Or a plate falls on the floor and breaks apart into 4 pieces. Those 4 pieces are part of the system. So all the objects in an interaction. I'm using that word interaction a little bit differently. So let's imagine, for this explanation, that we have a frictionless track and we have 2 cars on that track. Okay, and those 2 cars are touching one another. They're connected. And let's imagine that as if like 2 people were touching each other and connected. Let's imagine there's a tiny little spring. It has no mass. It's not part of really the system. It's just going to help us imagine these inanimate objects producing a force is between the 2. And when those 2 cars, and it's compressed, so when a latch is released for those 2 cars, the spring pushes those 2 cars apart. Similar to how I would push against someone else if I were exerting a force on them. Okay. Now, each of these 2 cars experiences a force. And how does that force relate to each other? Well, according to Newton's third law, they're equal and opposite. So the force that the blue car experiences, we'll call that force 1, is equal and opposite to the force the green car experiences. We'll call that force 2. And it's equal and opposite. So that is Newton's third law, the interaction between 2 objects. Now those 2 objects are interacting, and they're interacting for a certain amount of time. Well, that tells us that their impulses might be related. So if 2 objects interact, and we're just using these 2, they do so for the same time. They're in contact for as long as they're in contact for. They're interacting for as long as they're interacting for. Well, that tells us that the force that object 1 experiences times time t is going to equal minus the force that object 2 experiences times that same time t. They're interacting for that certain amount of time. Okay? Well, that's an impulse. So we know that if they're interacting for that certain amount of time, they're experiencing the same force. Well, then their change in momentum, has to be the same. If their force is the same and their time is the same, their change in momentum has to be the same. So let's, an opposite direction. So let's pull that apart a little bit. Well, we know that the change in momentum of object 1 is going to be mass of 1, the final of 1, minus the mass of 1, the initial of 1. So the final momentum minus the initial momentum. That's our change in momentum. Similarly, we know that the change of momentum of object 2 is m2v final 2 minus m2v initial 2. Again, the change final minus initial. All right, well, this is just really based on the idea that these two objects are interacting for the same amount of time with the same force. I'm going to rearrange it a little bit. I'm going to pull all the finals over to one side and all the initials over to one side. Before I do that, I'm going to do a little bit more algebra, and I'm going to distribute this negative side. So we have M1 V final 1 minus M1 V initial 1 is equal minus M2 V final 2 plus M2 V initial 2. Okay, so I just distributed that negative sign across the change in momentum. Now let's distribute a little bit. Let's put all the finals on the left and all the initials on the right. So if M1 final 1, I have M2 final 2, it's subtracted, I'm going to bring it over, so that's plus M2 final 2. That is going to equal, well, I have, bring M1 over to this side. I should have done this in green just to be consistent. Let me just erase that so you know which is which by color as well. So M2 V final 2. I bring this one over. We have M1 V initial 1 plus M2 V initial 2. So that's just some algebraic manipulation. Let me just pull this relationship. I'm going to rewrite it as one equation. I have M1 V final 1 plus M2 V final 2 is equal to M1 V initial 1 plus M2 V initial 2. Well, now what does this look like? If my system are all the objects in the interaction, my system is M1 and M2. This is the final momentum of object of object 1. What am I doing? Let me start over. This is the final momentum of object 1. This is the final momentum of object 2. This is the initial momentum of object 1, and this is the initial momentum of object 2. The momentum of a system is the sum of its momentums. So this is the momentum final of the system. And this is the initial momentum of the system. That tells us that for the system, the final momentum and the initial momentum are the same. For the system, momentum does not change for the system. Any one object within the system, the momentum can change. But for the system, it does not. And this is the idea, a very important principle in physics. This is what is known as the conservation of momentum. It is one of our laws, our fundamental laws. It tells us that the momentum of a system doesn't change. The final equals the initial. Now, it's very important, like with impulse, that we identify what that final and initial is. And it is defined, and I kind of view this as this equal sign is really our interaction. So final is right after, immediately after the interaction. And initial is right before, immediately before, right before the interaction. Now it's important that we keep in mind that this is for the system. The system, all the objects added together, their momentum. Any one can change, but for the system it does not. All right, so that's the idea of conservation of momentum. We'll do a sample problem on how we utilize that idea, but fundamentally it comes from Newton's third law. All right, good job.